Hello and welcome to our team's assignment. In this we'll perform two experiments, one related to friction and one related to the Young's modulus of a beam. Starting off with the friction experiment, the experiment investigated the relationship between the angle of an incline and the coefficient of friction, which we know as the coefficient of friction equals the tangent of the angle of the incline required for the object to slip. In order to reduce a random uncertainty while conducting the experiment, we conducted the experiment 3 times and averaged the results to give the ones showcased. And here you can see the process of us doing that. The sources of uncertainty in this experiment are the inconsistency in the surface of the plane, the use of our hands to modulate the incline, and measuring the incline to only one significant figure. Unfortunately, this meant we had a relatively large uncertainty in this experiment, but thankfully we got the expected results. This experiment resulted in an average of 9 degrees steepness of incline, which we use for all of our calculations. Here are the free body diagrams which explain what is going on, and using the value of the mass of an iPhone 7, we calculated its weight force to be roughly 1.35 newtons, and then using trigonometry when the incline is 9 degrees, we then calculated the perpendicular reaction force and the friction force parallel to the plane. And we know that the frictional force is the coefficient of friction multiplied by the perpendicular weight force, so finding the frictional force lets us solve for the coefficient of friction. And we experimentally calculated the frictional force using force equilibria and a rotated coordinate system to give us roughly 0.21 newtons. Now we can solve for the static friction coefficient, and to do that we divide the frictional force by the reaction force, which gives us approximately 0.15, which is close to the expected value of the tangent of 9 degrees, which is 0.16. And for our second experiment, we're calling it the Young's modulus experiment. And this experiment's objective is to obtain the Young's modulus of a certain wooden beam by putting loads on it, measuring the deflection of the beam, and using the related equations to find the beam's flexural modulus, which is equivalent to Young's modulus in this case. And the equations we will use in this experiment is one to calculate the deflection under these circumstances for a rectangular beam, and it has that constant I, which we also calculated, and when we substituted I for 1 over 12 WH cubed, it gave the final equation, when simplified, L cubed F over 4WH cubed D. And what the quantities mean in these equations is E bend, which is equivalent to Young's modulus, which is the intensive quality that measures the stiffness of a certain material. L was the length between our two supports. F was the force applied in the direct middle of the beam. W was the width of the beam. H is the height of the beam. And D is the deflection of the beam due to the load that we applied. And this diagram showed what the quantities are in our experiment. And to make the calculations easier on ourselves, we further simplified the equation. We used the properties of the beam, being L is equal to 780 millimeters, W is equal to 181 millimeters, and H is equal to 12 millimeters. And what that gave when we substituted it in is E bend is approximately equal to 379 times F over D. We use 3 significant figures in this experiment as standard practice. However, the uncertainties in this experiment are quite large, so it is optimistic to use any more than 2 significant figures in our opinion. Also, to calculate the deflection of the beam, we use the equation D is equal to H0 minus H. And here is a very nice diagram to explain how we calculated D deflection, showing what H0 and H are. And here are pictures of us conducting the experiment. As we go through, you'll be able to see that the flex in the beam increases, and it was cool to see that real-life application of what we learned in class. And to make sure our calculated F, or load, was accurate, we measured all of the kettlebells on scales. And here's our table of results. Starting from the very left, we have the claimed mass of kettlebell, which was measured in kilograms, and our range was 8 to 24 kilograms, which we thought would be appropriate for this experiment. We then measured H0, which was the same for all experiments, and H, and then we used that to calculate D. And then we also used our measured values of the mass of the kettlebell and multiplied that by G to get the true weight of the kettlebell in newtons. And then finally, using the equation mentioned earlier, being E bend is approximately equal to 379 times F over D, we calculated 4 different values from our table of results, and they were relatively close to each other, closer than we expected. And then we averaged those results And that got us the final answer of E bend and the Young's modulus of the beam being 2.33 gigapascals. And here are some closing notes from our experiment. To reduce uncertainty while conducting the experiment, a hole was drilled in the center of the plank to make the load be as close to a point mass as possible, because that's what our theory we used required, and so it would be less of a distributed load, although in reality it would slightly be that, being one of our sources of uncertainty. Also, the plank was inspected before and after the experiment to check for plastic deformation, of which there was a negligible amount, which was good to see. I expected some plastic deformation, but luckily there wasn't any. And the sources of uncertainty in this experiment is that the stools, which we saw earlier, had rounded edges, so they didn't act as point supports. However, they were pretty good for what we had. And the ropes we used were slightly elastic, so it could have contributed to this experiment's systematic error.